Hey, welcome. We are live in period 6-7, graphing exponential functions. 7-8, period 7-8, sorry. Graphing exponential functions. We're going to graph today y is equal to 2x and then y is equal to 1/2 x. I'm going to show you here, we're just going to do a normal t chart like we usually do, x, y. And I'm actually going to do this backwards. I'm going to put 2 and 1 up top because I want to show you the progression. Mainly what this is doing is this is getting you ready for if you're going to take Algebra 3 next year, seeing what an exponential function looks like as a graph, and just a couple of tricks to help you along with maybe your SAT at some point. All right, so if I graph y is equal to 2 to the x, okay, now I'm putting in 2, so 2 squared gives me 4. 2 to the first is 2. 2 to the 0 power, anything to the 0 power is 1. Okay. And then 2 to the negative 1, bless you. 2 to the negative 1, 1 over 2, which makes this 1 over 4. So let's go ahead and graph this. I've been doing this. This is my third time doing this today, so if I go too fast, please let me know. And then I'm going to graph. Now, I'm going to fill you in on a little secret here. This line will never cross. I won't say never, but right now, the way it's graphed, it will not cross your x-axis. For Algebra 2 purposes currently, this is not necessary to know, but in the future, it might be, especially for like your SAT, maybe whenever you go into the next course. This line that it never crosses is what we call an asymptote. So that's what the graph of an exponential function is. Kind of going back to whenever I was saying about how, like, if you multiply to get your next number in your order for your x and y chart, how it's an exponential. Dividing is also a way of just multiplying by a fraction, kind of gives you the same feel. I'm going to move over to the next one here. I'm going to try and keep these both up the same. We're going to do y is equal to 1/2 x. I just want you to see the similarities and differences in this chart. Okay, I'm still going to go 2, 1, 0, -1, -2. So 1/2 squared is 1/4. 1/2 to the first is 1/2. 0 to the 1/2 is still going to be 1. And then I've got my negative exponent. That's going to flip my fraction. That's going to be 2 and then 4. So if you look at both of those T charts, they're really just opposites of what the first one is compared to the second one. So whenever I graph this, my graphs are actually going to flip. And again, I'll have that. It's called a horizontal asymptote. Just so based off of this, the one thing that I want you to kind of take away from it is there is a like shortcut method to describe basically all of the just standard exponential graphs with an XY chart. So I'm just going to call this Mr. Stew's exponential graph chart. It has such a cool name, doesn't it? So if, thank you, if you have the equation and maybe we just put in a b for x. So y is equal to b to the x. B meaning base. That's your base number. Okay, it's all about the base, Okay, so you make an XY chart of 1, 0, -1, or you could do it -1, 0, 1, doesn't matter. 1 with the exponent will always resort to being that base number. 0, anything to an exponent of 0 will always be 1, and then -1 will be 1 over whatever that base is. Okay, just a little shortcut to kind of help you along before you do transformations in that later on. Right? So that's part 1. Okay. Part 2 is about. Oh, thank you. Part 2 is going to be about compound interest. Before we do that, though, growth and decay, just to kind of give you an idea. When your b value is greater than 1, you see a growth. When it's less than 1, you see decay. So if you take a look at these, back up to these kind of functions, this is going upward, so it would be considered a growth in green. Blue, it's going downward, so it would be considered a decay. Right, that's part 1 of the notes. Part 2, we're going to talk about compound interest, which is usually everybody's favorite because it deals with money. How many of you like money? Okay, yay! Me too. Okay, money isn't everything, but try and do something without it. That's what my grandpa always used to say. Really tough. Thank you. All right, here is the formula that you need to know. Really, I'm going to shorten it. I'm going to say A, or your total amount, is equal to P, which is your principal. It's the initial amount that you have, times 1 plus R, which is your rate. We're going to put that as a decimal. You'll see it as a percent. N is the number of compounding periods per year, and T is your number of years. So essentially, maybe, I don't know, anybody want to volunteer real quick? Ian has maybe $100 in the bank. It is compounded maybe 1 time a year, and the rate that the bank is giving him is crazy, like 5%, which doesn't really ever happen. That by plugging all that information into the formula, we'll be able to tell how much money he's gaining at the end of the year, which is pretty cool. A lot of times, if you go to banks and you have like a checking or savings account and they offer you interest, they'll use something called compounding continuous, which is very similar to this formula that we're going to use. So example 1 says find the final amount of a $500 investment after 8 years at 7% interest compounded annually, quarterly, monthly, and daily. Okay. First off, I'm going to rewrite the formula. I'm just going to make it A. A is equal to P times 1 plus R over N to the NT. Now, the $500 investment, that's my P value. The 7%, that's the R, and we're going to write that as the decimal, so 0.07. The time that it takes is 8 years. And then the compounding stuff is the other annual, monthly, daily, quarterly type of thing. All right. So let's break this up into four different problems. So annual. Does anyone know what annual means? Yearly. Okay, so 1 time. So in this case, I'm going to plug this into my equation. A is equal to 500 times 1 plus 0.07 over 1 times 1 times 8. So plug in that into your calculator. Just show you here. I like to put I like to make sure that I have my fraction in parentheses. So I'm going to put in 500 parenthesis, 500 parenthesis 1 plus parenthesis 0.07 divided by 1 parenthesis parenthesis and then my exponent, which in this case is 1 times 8. Now, some of you obviously know 0.07 divided by 1 is 0.07, and 1 times 8 is 8. But for the sake of the problem and how you'll plug in other things that aren't 1, I just want to show you the setup in your calculator. And then that will give you your answer. Now, if you're using a different type of calculator, it might not necessarily put your exponents together. You might have to put your exponents in parentheses, especially those of you with like a TI-83. Okay. The way that would look then is just parenthesis 1 plus parenthesis 0.07 divided by 1, parenthesis, and then it would be the little caret, little up arrow thing, and then I would put parenthesis 1 times 8, parenthesis. Either way, you're going to end up with 859.09. All right. Next up is quarterly. Quarterly means 4. So now I'm just going to plug that into my equation. Same equation. But now the 0.07 is divided by 4. My exponent, where n was, is going to be 4 times 8. Then you can plug it back into your calculator. So 500 times 1 plus 0.07 divided by 4, parenthesis, exponent, 4 times 8. 871.11. Though it was originally 1 because we said annual, it's going to be 4 times 8 because it's now quarterly. We'll have to put that there too. 871.11. See if you can do this for the remaining 2. Monthly, which means that your n is 12. And then daily, which means n is 365. Bless you. If anybody gets an answer for monthly, please feel free to share. Or daily. All right. So for the 12 months, you should got $873.91. And then anyone get 365? Yep, Caleb. $875 and what did you say? 29 cents. Thank you. Okay. All right. What do you notice about the amounts? They keep going up. So the more you compound something, the more money it's going to be generated, more interest is going to be generated, and the more money you're going to end up with in your investment. All right, so that is part 2 of our notes about compounding. Part 3, I feel like, is just the most abstract part. It's something that makes you kind of think back to your exponential rules. So before we kind of start, let's go over a little bit of those exponential rules. If I have 4 to the negative 1, that can become what? If I have 4 to the negative first, becomes 1/4. We flip it. Same thing if I had 1/4 to the negative 1 would also then become 4. Does anybody remember what happens when we have a fractional exponent? So say I have 4 to the 2/3. Put the exponent out front. The denominator is the part of the radical. And then we would write 4 squared on the inside. Or vice versa. We could flip that around. If we had the radical first, then we could make it into an exponential fraction. Which leads me into solving exponential equations. So the way that you solve exponential equations, the very first thing you want to do is look for a similar base. So 125 and 25 both have what base exponent in common, or base number? 5. Good. 5. Because 5 cubed is 125, and 5 squared is 25. So now let's change those numbers into 5. So 125 becomes 5 cubed x. And over here on the other side, we've got the cubed root of 5 squared. Just as a reminder, take a look at up top what I circled in red. What happens to that radical is it becomes a fractional exponent. So from here, we can then have 5 to the 3x is equal to 1 over 5 to the 2/3. Now to make it so that they're on the even playing field, I need to move this bottom fraction up to my numerator. In order to do that, I've got to do something very similar to the next thing that I'm circling, whereas I have to take essentially and create a negative exponent. So 5 to the 3x is equal to 5 to the negative 2/3. Now mathematically, because now they have the same base, we can cross out the bases and solve the exponents. So we'll be left with 3x is equal to negative 2/3. Divide by 3, and I get x is equal to negative 2/9. Like I said, this is the more abstract part of the notes for today. I'm going to walk you through the next two examples, and then after that, we're done. Take a look at example number 3. What base do 27 and 9 have in common? Yeah, I just gave it away. Doggone it. All right, so 3 and to the third times 3x minus 1 and 3 squared times x plus 2. Now that they both have that same base, we can eliminate the bases and solve the exponents. So 3 times 3x minus 1 equals 2 times x plus 2. So now I have 9x minus 3 is equal to 2x plus 4. Subtract 2x. It's 7x minus 3 is equal to 4. Add 3. Some of you could probably do both those steps at the same time. That's fine. And then divide, and you get x is equal to 1. Thank you. Give you a second if you're copying anything down, and then we're going to head to the very last example here. All right, example number 4. So this is one of the more complex ones just because of the bigger numbers. I'm going to give this to you that 8 cubed is 512, and 11 cubed is equal to 1331. So I'm going to leave this side as is, 11/8 x minus 4. And this side I'm going to make into 8/11 to the all to the third power times 2x plus 1. Once again, both of these are flipped. So I'm actually going to flip this fraction. And when I do that, this now becomes a negative 3 on the outside. Now they both have the same base, so we can solve the exponents. The key is, no matter how complex, is to get the same exact base on both sides. So distribute negative 6x minus 3. I'm going to add 6x over to both sides. 7x minus 4 equals negative 3. 7x is equal to 1. And then x is equal to 1/7.